We're going to continue talking about solutions today.
96 on the
And we've already gotten through a good part of the learning goal and you've been assessed on it. Most of your quiz scores were quite good. Today what we're going to be getting into is calculating boiling points of solutions, talking about why the boiling point of the solution is greater than the boiling point of the corresponding solvent. Later in the week we'll be getting into freezing point temperatures, and we'll talk about why they salt roadways up north when it snows, why when the temperature is going to dip below 32 degrees Fahrenheit down here, farmers have to protect their crops. And then finally we'll get into molar masses of solutes that have been dissolved in solvents. So you'll be using freezing point or boiling point information of a solution to calculate the molar mass of a solute in the long run, and it's from solution data. So we're going to pick up here in our notes, and what we're really going to be looking at today is why the boiling point of a solution is greater than the boiling point of its corresponding solvent. And so, for example, if you had a beaker with water in it, and you put it on a hot plate, and you have a thermometer in there, you know that water boils at 100 degrees Celsius. Now if we take a closer look at the water at the molecular level, we've talked about Lewis dot structures this year, and you know that water has a bent design. You may or may not recall the bond angle of 104.5. You also will recall that you don't just have one water molecule in there, but a lot of water molecules. And these water molecules link to one another through intermolecular forces. Now, water is a polar covalent molecule. It has London dispersion forces. It has dipole to dipole forces. And what would we call this interaction? Hydrogen bond. When water boils, those intermolecular forces are broken or severed, and the water molecules go their separate ways, and water can transition from the liquid state to the gaseous state. If it's open, the gas molecules will just leave. If it's closed, then the gas molecules will be above the liquid molecules, exerting pressure on the walls of the container. The boiling point of water, a solvent, is 100 degrees Celsius. The boiling point of a saltwater solution will be greater than 100 degrees Celsius. At a certain temperature, the intermolecular forces will be broken, and the water in the liquid state will transition to the gaseous state. When you add solute to solvent, it's almost as if you create a traffic jam, and it is more difficult to break these intermolecular forces, and as a result, the boiling point of a solution will be greater than the boiling point of the solvent from which it's made. So the boiling point of a solution is greater than the boiling point of its corresponding solvent. When you make pasta, you don't just throw pasta in boiling water. You usually throw pasta in boiling salt water. And a chef will tell you it tastes better, and it does, but it also cooks at a higher temperature because the salt water boils at a higher temperature than water alone. Boiling point elevation is one colligative property that we are going to introduce here. Generally speaking, with colligative properties, you will see that the solvent's properties are changed when a solute is added. One change is that the boiling point gets higher, another change is that the freezing point gets lower. The properties, that is colligative properties, are determined by how many particles you have in solution. We'll talk about that. That's determined by whether you have a covalent or an ionic substance. And if you have an ionic substance, you need to calculate how many ions are present based on a balanced equation. It's also determined by concentration, not by the type of particle. You'll see for boiling point elevation and freezing point depression, the way we're going to use concentration is with molality, moles of solute per kilograms of solvent. Osmotic pressure, we're not going to get into at the honors level, but that's dependent on molarity. And vapor pressure depression, we're also not going to get into at the honors level unless you want to. This is an exceptionally bright class. You may want to explore it a little bit more. And that is based on mole fraction, and that's one of the reasons I showed you all the different ways that concentration can be expressed. We're going to focus on boiling point elevation and freezing point depression. Today we'll just do boiling point elevation and then just a wee little lesson on freezing point depression. With boiling point elevation, again, you're going to see that there is a temperature difference between the boiling point of the solvent and the boiling point of the solution, and we'll take a look at that. As I mentioned, when you add solute to solvent, it acts as a accident, if you wish. I guess you don't want an accident. If you'll think of it that way, it just really slows the flow from the liquid to the gaseous state, the same way an accident would essentially stop or slow the flow of traffic. And as a result, the solution requires a higher temperature to boil. As I mentioned, the boiling point of the solution is greater than the boiling point of the solvent. If you understand that, the formulas that you use will make sense, especially the second of the two you're going to use. Two formulas you're going to see highlighted in green. The first is that the change in boiling point, that is the difference in the temperature at which the solution boils and the solvent boils, is equal to the molal boiling point constant. The molal boiling point constant is found on table 2 of your second semester periodic table, and you'll see that right here. Second semester periodic table. Here's table 2 here. We've got different solvents: acetic acid, benzene, camphor, cyclohexane, right down to water. Benzene is a nonpolar covalent solvent. Water is a polar covalent solvent. The molal boiling point constant is shown right here. It has a funky unit, but you'll see how it cancels nicely. It's degrees Celsius times kilograms over moles, or degrees Celsius per molal. You can do it either way. I can show you both. Acetic acid has a molal boiling point constant of 2.530 degrees Celsius per molal. Benzene, 2.53 degrees Celsius per molal. Water has a molal boiling point constant of 0.515 degrees Celsius per molal. So for boiling point type problems, we'll be using these first two columns. You'll see later on for freezing point, we'll be looking here. So I want to know what my solvent is. Let's say it was camphor, and in this instance, I'd have the boiling point of camphor alone and the molal boiling point constant for camphor, and I'll show you how to use those. But that's the first piece of Formula 1. The second piece is that you multiply it by the molality. You've seen molality already. You've been assessed on it. Moles of solute per kilogram of solvent. If they give you grams, you move the decimal 3 to the left to go to kilograms. Some kids were a little cockeyed with that on the quiz. I is the Van Hoff factor. This is how many particles you have in solution, and I'll show you how to determine I very carefully. If you have a non-electrolyte, this is a substance that's not going to break up into ions. So you're essentially going to have one particle, if you will. So these are your covalent compounds, and they often start with carbon. These are your sugars: glucose, C6H12O6, sucrose. Non-electrolytes, I is 1. And on the classwork, I think I told you when I was 1, I kept it simple. I'm not going to do one of those with you because they're much easier. And I is 1 for a covalent compound. For your electrolytes, and these are your ionic compounds for the most part, provided that they're water soluble. All group 1 ion containing compounds are water soluble. All nitrate ion containing compounds are water soluble. All acetate ion containing compounds are water soluble. So these are going to be your electrolytes, and they will dissolve in water to generate ions. And let's take a look at how you determine I. I'll walk through a few examples, and you'll see more in the examples that we do to calculate boiling point of the solution. Let's say, for example, that you have sodium fluoride, a solid, and you are going to dissolve it in water. Sodium fluoride generates sodium ion. Ions are aqueous. And fluoride ion, I, is equal to the number of particles in solution, or it's easy to determine I. It's equal to the sum of the coefficients of ions. And so 1 plus 1, I is equal to 2. This one's very easy because it's a binary ionic compound. But again, you could do something like
I got it.
lithium sulfite. You've got lithium ion, and you've got sulfite ion. Thank you. Can I do this in a little while? I'm sorry. Lithium ion and sulfite ion, and make sure you balance for charge and for atom. So what would I be here? Three. And let's say you had something like cesium phosphite. How would you determine I? So you have cesium ion group 1, 1 plus, phosphite ion, and I know you were not required to memorize your polyatomics this year. For those of you moving on, it would be a good idea to get a good beat on it now. Balance, so I here would be. And I really can't think of an instance where I is going to be much more than 5 or 6. So if you get an I of 20 something, you've made a mistake. So that's how you determine I. And when you determine I, be sure to write this equation showing the dissolution of a solid when dissolved in water. So this is a dissolution reaction. It's not GORD. You can say dissociation or dissolution. It's not decomp. Decomp generates elements or compounds, not ions. You're going to be generating ions. So that's how you determine I. And now you have all the pieces you need for this first formula. Kb based on the solvent, molality, which you know how to determine, and now I. Once you calculate the change in boiling point, to get the boiling point of the solution, you will add the boiling point of the solvent, which is given on the back of the periodic table, plus the change in boiling point. You add it because the boiling point of the solution is elevated, so you have to add these together. So using these two formulas, we'll be able to calculate the boiling point of the solution. And we're going to walk through two examples very closely, and I think you'll be very comfortable with these types of calculations. Questions here? Looks good? All right, let's give it a rip. It says, at what temperature will a solution of sodium chloride boil? So they're asking for the temperature at which the solution boils. So they're asking for the boiling point of the solution. We have 120 grams of sodium chloride, and it's dissolved in 1,300 grams of water. So that's all the information they give us. Let's get it down. It doesn't seem like it's enough. Yet you'll see as we walk through the two formulas, you have everything you need to calculate the boiling point of the solution. So in this first example, we're looking for the boiling point of the solution. The mass of the solute is 120 grams of sodium chloride, and the mass of the solvent is 1,300 grams of water. My first formula is that delta TB is equal to KB times the molality times I. Where do we get KB from? Back of the periodic table. What's our solvent? What's our solvent? Water. So we look at water, and our molal boiling point constant is right there. 0.515 degrees Celsius times kilogram over mole. How do we get molality? We need moles of solute, so we're going to convert this to moles. So we have 120 divided by 58.443, and that's 2.05 moles of sodium chloride. So do we just plug that in for molality? You better not, because what do we need to divide this by? Kilograms of water. Move the decimal 3 to the left. So we have 2.05 divided by 1.3 is 1.58 moles over kilograms. Now we have to get the I. Do we take our solute or our solvent? What gets dissolved? Solute. So we take our solute. That's going to generate sodium ion and chloride ion balance. So my I is 2. Now that 2 is important to calculate delta TB, but it's not important for significant digits, so stay with what you were given here. You have 0.515 times 1.58 times 2, and that's 1.63 degrees Celsius. That's my delta TB. That means that the boiling point will increase by 1.63 degrees Celsius. And note this unit cancellation here. You have moles, you have kilograms. You're left in a unit of degrees Celsius. And if you don't like writing all that out, instead of showing this unit, for the KB, you can do degrees Celsius per molal, and then for molality, you can use the M, and you can cancel that way if you prefer. Whatever rocks your world is fine. So your delta TB is I gave it away. Your delta TB is 1.63 degrees Celsius. Your boiling point of the solution is the boiling point of the solvent plus delta TB. And I got ahead of myself because I started to yell out the answer before showing it carefully. When you add or subtract, you go to the least number of decimal places. So the temperature at which this salt water solution boils is 101.63 degrees Celsius. So again, two formulas. Here's the first. Don't forget to calculate the molality. If you just use moles, you're not going to get your units to cancel and your temperature's going to be off. Here's your delta TB. The boiling point of the solution gets elevated, so we're going to increase the boiling point of the solvent by the delta TB by adding the two together. The solution boils at 101.63 degrees Celsius. So nothing there is terribly difficult. It's just several steps that you want to keep track of. But if you work it very carefully, I think you'll be quite successful there. Questions on number 1? Let's pull the information out on this last problem. So on this second problem, it says at what temperature will a potassium sulfate solution boil? So we want to know the boiling point of the solution. We have 121 grams of potassium sulfate, and it's dissolved in 708 grams of nitrobenzene. Let's take a look. And when you do your first practice problem or your first couple, if you have these steps in front of you, I think you'll be more successful. Again, you want to know the boiling point of a solution. The mass of the solute is 121 grams of potassium sulfate, and the mass of the solvent is 708 grams of nitrobenzene. I believe I wrote the chemical formula for nitrobenzene on the back of your periodic table. It looks kind of cool. That's what nitrobenzene looks like. All right, what do we do? What do we do? What's our first formula? Delta TB is equal to what? KB times molality times I. So what should we do? You want to convert mass to moles? Solute or solvent? So we'll get the formula mass of potassium sulfate. So should we just plug the moles in here? Is M for moles? You better not. What are you going to divide this by?
Mass and solute.
In kilograms, right? Alrighty. What's KB? What are we going to, where do we even find that?
Table 2.
Table 2 back. So what's our solvent? Crazy nitrobenzene, right? So are we going to use that? 5.24 degrees Celsius per molal. Our molality is equal to 0.980 moles per kilogram. Ooh, we have to get I. How do we do that? Solute or solvent? Solute. What ions do you get? Potassium ion and? Should you break up the sulfate ion? You better not. What's I equal to? 3 is correct. So, delta TB, that is the change in boiling point, is 15.4 degrees Celsius. Is that my final answer? Heck no. The solution boils at, we're going to add the solvent, and what's the solvent for nitrobenzene? 210.8, right? And we'll add that to 15.4 degrees Celsius. Again, note that unit cancellation getting you to degrees Celsius. You have 210.8 plus 15.4. Maintain that decimal place is 226.2 degrees Celsius. So when finding the boiling point of the solution, you first find the delta TB by multiplying the KB, the molality, the I. Once you get it, you add it to the boiling point of the solvent. Question?
How do you know how many sig figs to do?
In regard to Siggy Wiggies, here I was given everything in 3 sig figs, so I stayed there and kept it there. This number here tells you I, but it's not relevant for significant digits. So I transferred 3 sig figs down here, and when I add or subtract to go to the least number of decimal places, these are both to the 10th place, and so I maintain the 10th place. All right? So this is boiling point elevation. Another colligative property is freezing point depression, and though we're going to finish here today, I want you to think for a minute. Your freezing points for your solvents are shown here. Here's your molal freezing point. How might freezing point depression differ from boiling point of the solution? How do you think this formula might differ? Instead of KB, you're going to use KF, and instead of adding, you will subtract. And we'll get into freezing point depression, another colligative property, tomorrow. It's grossly similar. It's very, very straightforward. In your classwork, I had you work the both types at the same time. I just figured you didn't have to calculate 100 different molalities. I was trying to make it easier. Numbers 15 through 19 require both a boiling point of a solution and a freezing point of a solution. And you will be a lot more successful tomorrow with the freezing point of the solution if you work these problems for boiling point of solution before then. Really keep track of your molality because you'll need it for the freezing point section. But boiling point elevation is just one type of colligative property that you can talk about. We'll talk about freezing point depression, which really has more practical applications in regard to snowstorms up north, which they seem to be experiencing a lot of this winter as we sit in the sunshine. And then we'll talk a little bit about why, especially out in the glades, they worry about their crops if it gets cooler down here. When I mean cooler, I mean below 32 degrees Celsius. But we'll talk about that tomorrow. Any questions in regard to boiling point elevation? If you do those problems, you will be highly successful with this section.